Now we've defined a lot about random signals, what they are, some limitations such as wide sense stationarity that makes a lot of things easier. Now it's time to look at what happens when we actually use random signals in a signal processing system. So we're going to start by filtering random signals with an LTI filter. So we're also going to assume that X is stationary. Or not quite as restrictive, X of n is wide sense stationary. So we have this system above. Question number 1 is, what is the mean of y? Well, this is going to be equal to the expectation of the convolution of x with our system having an impulse response handily already provided of k. Now the expectation is linear, and we have a linear system, so everything plays wonderfully together. And we can swap the order. I don't know if you recall, but a little while ago I talked about tricks in signal processing. And one of the greatest tricks in signal processing is to simply change the order of operations. And so we'll do that here. Now, since we have a stationary x, it doesn't matter what n is or what k is. This is just going to be the mean value of x, giving us mx, which factors out, times the sum over all k of h of k. There we are. Okay. Question 2. What is phi yy of m? This is going to be a little bit more involved. So our autocorrelation function is going to be the expected value of y n plus m times y of n. Well, this will be the expected value of the product of the convolution equations. So we now use our favorite trick of swapping the order of operations, and we'll use our other favorite trick of doing a change of variable. So by choosing r to be equal to L plus k, we're essentially expressing r in terms of an offset to k, which simplifies things a little bit, but it may not be obvious at first. Since we're summing over all time, our sum over r now becomes a sum over L inside of k here. And we can move the expectation inside, and we get a massive term for our argument here to x, and the h's, while still being encompassed by the sum, are not inside the expectation. It does get better. So we can now recognize this term right here. It looks like an autocorrelation term, but getting a handle on that is a little bit tricky. So if we put the n minus k and have that be our independent variable, then the offset we're giving is plus m minus l. So this is just going to be phi xx of m minus l. And then while we're at it, this is getting cumbersome, so we're going to define this as c h h l. It's just a definition. This looks a lot like a autocorrelation function, and it's going to be the sum over k of hl plus k times h of k. I think I'm going to need to give myself a little bit more room so that when you print the notes it doesn't try to print it onto a second page. There we go. So now we can express our whole autocorrelation of y as the sum L equals minus infinity to infinity of phi m minus l of xx times chh of l. Okay, well, what did that buy us? That helps, but it's a little bit less satisfying because while this phi xx of m minus l might be pretty obvious, we still have to calculate this chh. This chh looks like what we call the deterministic autocorrelation of h. In other words, it's the same type of operation, except instead of an expectation, we have a sum. And so that's why we have notation that's very similar there.
I found this on the web for the CHH looks.
So we have a final step that will bring this all together, I think, in a way that is pretty elegant. What happens if we take the DTFT of phi yy of m? Remember, this is the power spectral density phi yy e to the j omega. Well, looking above, let's look more closely at what we just did. Phi yy is equal to, and that's a convolution of phi xx with chh. So if it's a convolution of cxx with chh, phi of xx with chh, then taking the DFT will turn it into a product. It'll be a product of the DFT of xx, which we've already defined as that, and this new quantity that we define in this manner. Okay, so we're getting pretty close, but we're going to spend just a moment more and look at what is capital CHH. Well, CHH e to the j omega is equal to the DT/FT of the sum over k h L plus k h of k. Forgot the conjugates there. Okay, now we've got the conjugates. Well, this is just equal to the DTFT of H of L convolved with H star of minus L. I did the change of variables there in my head, but you could go ahead and work it out if you like. Well, the DFT of a convolution is a product. So this is going to be H e to the j omega, and the second term is H star e to the j omega, giving us magnitude of H e to the j omega squared. Thus we have the result that the power spectral density of our filter output is equal to the power spectral density of the filter input times the power spectrum of the filter itself. And so filtering random signals now makes sense from an intuitive point of view. We can do frequency shaping on random signals just as we can on non-random signals, and everything fits together just well.